paper we will discuss today is Overview of the SPARC tokamak. Abstract. The SPARC tokamak is a critical next step towards commercial fusion energy. SPARC is designed as a high-field B equal 12.2 Tesla compact, R equal 1.85 meter, A equal 0.57 meter. Superconducting DT tokamak with the goal of producing fusion gain Q bigger than 2 from a magnetically confined fusion plasma for the first time. Currently under design, SPARC will continue the high-field path of the Alcator series of tokamaks, utilizing new magnets based on rare earth, barium, copper, oxide, high-temperature superconductors to achieve high performance in a compact device. The goal of Q bigger than 2 is achievable with conservative physics assumptions H equals 0.7 and with a normal assumption of H equals 1. SPARC is projected to attain Q equals 11 and P equals 140 megawatt. SPARC will therefore constitute a unique platform from burning plasma physics research with high density N equals 3 times 10 to the 20 powers per meter cube, high temperature T equals 7 kilo electron volt, and high power density P per V equals 7 megawatt per meter cube, relevant to fusion power plants. SPARC is placed in the path to commercial fusion energy. Its parameters and the current status of SPARC design work are presented. This work also describes the basis for global performance projections and summarizes some of the physics analysis that is presented in greater detail in the companion articles of this collection. Chapter 1 Introduction. The world faces an increasingly urgent need for clean energy, as the effects of climate change are already manifesting and existing portfolio of clean energy sources has not been developed quickly enough to broadly reduce greenhouse gas emissions. Fusion energy is one possible solution to this need, but it must be developed and deployed rapidly in order to make a difference on the time scales necessary to have an impact on climate change. Fusion is safe, energy-dense, and dispatchable, produces to greenhouse gas emissions, and generates minimal radiological waste. Also, the plasma physics governing fusion devices is relatively well understood. No fusion device has yet demonstrated gain Q bigger than 1, which is a critical step on the path to commercializing fusion as an energy source. Achieving fusion gain Q bigger than 1 in a magnetic confinement device has long been the aim of fusion research around the world. Recently, several studies have also emphasized that construction of a pilot fusion power plant should be a near-term priority of fusion research in the USA National Academies of Science, Engineering, and Medicine 2019, American Physical Society Division of Plasma Physics, Community Planning Process 2020. Beyond demonstrating Q bigger than 1 and constructing a pilot power plant, however, it is vital that fusion's path to commercial power generation be both timely and economical if the goal is to transform the energy economy and combat climate change. This motivation led to the founding of the SPARC project with two central mission objectives. The first is to achieve a fusion gain Q bigger than 2, demonstrating fusion energy production from the plasma with margin over break-even Q equal 1 as a critical next step on the path to commercial fusion energy. If SPARC exceeded this goal and achieves higher gain, it will also address many novel changes in burning plasma research, including burn control, burning plasma, self-organization, alpha particle, magneto-hydrodynamic (MHD) mode interactions, diverter physics, and disruption prediction and mitigation. Second, it is SPARC's mission to demonstrate the viability of rare earth barium copper oxide (REBCO) high temperature superconducting (HTS) magnet in an integrated fusion confinement facility, thereby paving the way for future power plants based on this technology, such as the arc power plant concept. Sabon 2015. The SPARC project aims to show that the high magnetic fields possible with REBCO-based magnets allow one to reduce the size of fusion devices and facilitate rapid and lower cost progress. SPARC's focus on high magnetic fields and compact size is an extension of what is often called the high field path to fusion energy and is based on the same principles as those that led to proposals for high field copper devices such as CIT, BPX, FIRE, and Igniter. The high field path and SPARC's place in it is described further in Chapter 2. SPARC's use of REBCO superconductors also builds upon the legacy of past designs that focused on high magnetic field, including VULCAN, ARC, and designs by Tokamak Energy, in line with the focus on high magnetic fields and new magnetic technology. It is a philosophy of the SPARC project to design a machine based on conservative, well-established physics assumptions and to lay on innovative engineering and technology to minimize the size and cost of a Q bigger than 2 device. Performance projections for SPARC, which are described further in Chapter 4, are based largely on the ether physics basis, and SPARC is designed with considerable margin in plasma performance in order to ensure that the machine's mission is feasible even given the uncertainties in performance projections. SPARC's engineering design also builds on the work of many other machines and design studies, including experience of past DT devices such as TFTR and JET and designs for ITER. The remainder of this article, which is the first of a collection describing the status of and work to date on SPARC, will address the following. First, Chapter 2 describes where SPARC fits into the greater fusion ecosystem and how its design came about. Next, Chapter 3 presents the measure SPARC parameters and the machine cross-section. Section 4 then discusses the methodology used to project SPARC's plasma performance and describes the projected performance in several operational scenarios. Finally, Chapter 5 introduces the other major physics analyses that have been performed for SPARC V2, including work on core confinement, H-mode access, and pedestals, diverter physics, MHD, and disruptions, radio frequency heating, and alpha physics, many of which are presented in greater detail in other articles in this collection. Thanks for listening to the end of today's show.